All right. So today we're gonna continue with what we left. We were left last week. Uh, so last week's lecture was about Rabi oscillation, and we had to finish early because we ran out of time. So this week we will continue with Rabi, and then we will transit to Ramsey. Yep. All right. So just let me first write down the formal Rabi oscillation, the complete Rabi oscillation. I think I've done this last week, but let me just do it again. Rabi model. You know what? Let me just use some shorthands because that's faster. Okay. All right. So this solution to the Rabi model is crucial to every discussion that we will have today. So this is G, this is E, this is that, all right? And for notation, the electromagnetic wave is this. Um, okay. All right, so this is an important equation. And let me just add that this is defined. This and S. All right, good. So that's pretty much everything we need. Okay. Yes. All right, that's all. All right. So if we have a system that was initially in the ground state, right? And then we offer it a pulse, an excitation, you'll be excited to the excited state, right? And the probability of it going to the excited state goes like a sinusoidal. Remember? Okay, so this is probability, and probability is CE squared. Okay. Now, we said last time that when it reached the peak, I don't know if I say this last time, but when we reach the peak, this is called the pi pulse time. Okay, T pi, and so this is 100% probability that you will find the state, the system in the excited state. But when it reached the 50%, this is what we often call pi over 2 time. Pi over 2 time. All right. Now, there are a few factors that will that we can use to control the periodicity and also the height. Remember? And last week we covered so we talked about the dependence in the Rabi frequency because so this is the function. So this function is this PE. This function is this. Okay, so you can see that the periodicity from here to here, from one peak to the other, this is 2 pi over capital omega. Yeah? Is it? No. Yeah. Omega is. This is 2 pi over capital omega. No, this is pi over omega. I mean, I'm sorry. Who can tell me what the periodicity is? 4 pi? Really? I know it's supposed to be 4. No. This is okay, let's say, so at this point, you have pi t over 2 equal to pi, right? And the other one is pi t over 2 pi. Okay, so the difference is 2 pi, right, guys? So the first peak occurs on this face, right? Yeah. And the second peak is this, right? So the difference in time, t1, t2. The difference in time. Wait. Yeah. Right? So tau t is 2 pi over. Right? Okay. Yeah, don't be fooled by this. So normally you will write this divided by the frequency here, right? But that's when you are dealing with cosine. If you have cosine square, then the periodicity is doubled and the period is half. Okay, so that gives you this. All right, so this is just a little recap. So from peak to peak, we know it's controlled by this omega, this capital omega, and this is called the generalized Rabi frequency. While this thing inside, this modulus chi, this is called the Rabi frequency. Okay, and the Rabi frequency is related to the interaction Hamiltonian, so which I use V. So VEG is the transition, basically the strength of the transition from G to E. Okay, so that's the interaction coupling strength. So this is how chi related to the interaction Hamiltonian, and that interaction Hamiltonian affects the periodicity of your Rabi oscillation. Okay, you could also think of this oscillation not as a probability oscillation, but the energy oscillation in the system, because energy is just the probability times the energy, right? So if the energy here, we call it 0, and this is h bar omega 0, then the energy of the system will be Eg times Eg plus EE, and then that will be Pg times 0, Pe times h bar omega, right? Okay, so you can see that the energy, the oscillation probability is the same as the energy oscillation of the system. Okay, so you can understand this as an oscillation in the system when you offer an excitation drive, and this oscillation become faster when you increase the coupling strength. In other words, if you increase your microwave. Oh, that are just jargons for quantum information processing that we will talk about later. Just remember the yeah, this is ground state. This is no yeah yeah. If you like, this is 2 pi. This is called, okay. So this is the angle related to the Bloch sphere representation, which we will cover later, not today, okay. But just remember that often we call the peak, okay, the time it takes to reach the peak. That is the time, that's the pi pulse time, and the other, the 50% is pi over 2, okay. All right, now like I said, so increase the strength will give you a faster oscillation because the efficiency of pumping energy into the system increase as the photon flux increase in your driving field, right? If there are more photons present around your field, around your system, there are more chance for photons to be absorbed. Therefore, it takes shorter time to reach to a maximum energy, right? Now, there's also a dependence here called detuning, which is highlighted here. This is called detuning. Notice the notation I use might be different from some textbook. Some textbook might have delta defined as omega naught minus omega. But this is a definition I think that make more sense to me as an experimentalist, so I'm gonna stick with it. So anyway, there are two things that depends on this. Because if you just look at this, you might find it strange that a larger detuning when you are off resonant, when you drive the system with a wrong frequency, it seems like the effect is the same as increasing the drive strength, and that's kind of strange, right? But if you also notice that here in the maximum, when you increase the detuning, this also dropped. Then you will see that this actually becomes like this. Okay. So the red is when the intensity of your drive increase, and the blue is when the detuning. So when the detuning increase, when you are driving the system with the wrong frequency, okay, it will reach to a lower value because, like I said last time, when you drive it with the wrong frequency, within a certain amount of time, you can go from pushing the system. Remember the example of a swing, of pushing a swing. You will go from pushing the swing from pushing against the swing, doing negative work. And the more detuning you have, the more frequent this pushing against occurs. Okay, so that's why the efficiency actually gets lower. It wants to increase. At first, it wants to increase energy, but then it cannot follow. So it kind of just slip off. Okay, so this is like a slip off. The interpretation of this is a slip off. Okay. Okay, now there's another thing I want to point to concerning this formula. Let me just write it down. So if I just write down, so if I fixed my pulse duration, okay, so if I have a fixed pulse duration and I call it tau, yeah, then I'll just put tau as the probability at the end of my pulse will be t equal to tau, okay, and so this oscillation part is fixed at some point. At some point, I did not specify whether this will be the maximum or halfway. It doesn't matter. What matters is this is a fixed number, right? Now, okay, let me just simplify this. So say if on resonance, I drive the system to its peak, okay? I choose tau to be equal to tau pi, to be the pi pulse duration, okay? Then when I am at resonance, when I'm at resonance, I naturally have 100%, right? But what happened if I change, if I scan the frequency of my laser, sorry, my microwave. If I scan the frequency of my microwave for the same amount of time, what happened is that you will get a profile like this. Okay, a profile like this, and this pretty much agree with this, pretty much. This pretty much agree with this, and this is a Lorentzian. This is called a Lorentzian line shape. Lorentzian.
So the x-axis is the frequency here, or yeah, indeed you mean.
Lorentzian line shape. Okay, this is called a spectrum line shape. This is what I call Rabi spectrum. Rabi spectrum. Okay. All right. Of course, this value will change too. Okay. This value will change too, so it's not completely determined by this form factor. Okay. So this value will change too, right? Because if I use the pi pulse duration if I use the unresonance pi pulse duration, it is not the pi pulse. It is not the pi pulse duration for off resonant drive. Let me just write this out for you. Let me show you. So I'm just writing this factor out. Okay, And if I use tau, if tau is the pi pulse duration, that means it's the unresonant pi pulse duration. That means this times this equal to pi. Okay, so tau equal to 2 pi. I mean, yeah, it's basically just this. Oh, sorry, it is pi. sorry. Pi. Zero. No. This is sine. I'm sorry. I started with 0, so it should. I'm sorry. This is sine. Okay. So yeah, this is the maximum. Get it? The periodicity is still 2 pi over omega. Okay, we don't need to worry about that. But the pi pulse duration is when this condition satisfied, and this condition is for unresonance. That means the detuning is 0, right? When the detuning is 0, then the generalized Rabi frequency is equal to the Rabi frequency. Okay, that's what's inside. And when this value equal to pi over 2, then sine square become the maximum, right? Yeah. So this is pi over that. Okay, so you can see that this is half of this periodicity. Yeah. Okay. Now I'm going to substitute this in. Sine. Okay. Oh. Right. So sine square. Okay. Okay, so that's pretty simple algebra here. You can see that when I have no detuning, right, then this will give the maximum value because this is pi. We have a pi over 2 here, right? This whole thing will be 1 if I have no detuning. But when I have detuning, then this is less than 1, okay? Yep. So what I'm trying to say is when you have detuning, here the full factor drops down because this becomes a small number. But also this factor here, it drops down too. Yeah. But nonetheless, let's just say qualitatively, this still looks like a rolling line shape, which is dominated by this factor. Okay. The line shape primarily is dominated by this shape. But of course, if you really want to be precise, then if you want to, for example, fit your data, then you need to put another factor of this to your fit. Okay. All right. So you see this factor. Yeah. Okay. So there are two dependents. Now, so say if you want to increase your signal, okay. So say even if this is 100%, but in the experiment, it could still be a small signal, right? And you have a lot of, say, fluctuations. You have a lot of fluctuation because you are close to the noise floor. This is called the noise floor. So this is always there, even if you're not turning on your microwave, right? This is called a noise floor that is just intrinsic to the apparatus. So say you have a low signal to noise ratio, and you want to improve it. What are you gonna do? If possible, I think you will try to crank it up, right? You will try to crank up the power to make it stronger, to make this stronger. Yeah.
Or decrease the retuning.
And indeed, it will go up. No. So say if you want to work with on resonance is not always a good thing.
Not exception.
It's on resonance. Sometimes we want to work with something that is slightly off resonant. Okay. For example, in Ramsey interferometry, you want to work with an off resonant drive. Yeah. So say that this particular value, this is useful to you, and you want to increase the signal here, right? And we know that here, from this, we know that with detuning, this is less than 1, right? So what do you want to do? You naturally will want to increase your power, right? If you increase your power, that can make this factor smaller, right? And maybe you will get closer to 1. Yeah, for this point. Okay, so say you do that. If you do that, then what will happen to this whole entire spectrum is that that the width of it will increase. Let me just exaggerate the shape. Like I said, this is not exactly a Lorentz line width. So maybe it'll become like this. Okay.
Just by increasing the microwave power.
Yes. Okay. So you see this. The width will be broadened. Okay. Yes, this is increased, but your width is also broadened. This is called power broadening. So is this effect?
2, right?
Huh?
F2 or 3.
Yeah. This effect is called power broadening. Okay. And what's the physical cause of it? Is that you see, let me just give you a straight answer for this. When we increased the power, right? When we increase the power, so say like we are here, off resonant, right? Now, if we increase the power according to, now we are in a detuned drive. If we increase the power, we know that the periodicity will get shorter, right? Because that same argument still apply, even though it is a detuned off resonant drive. But the same argument that there you have more photon flux, therefore a little more chance to excite, that argument still stand. So you can expect that this will go, for example, the efficiency will go better. For the same amount of time, you will have more, right? And also, when you have a stronger drive, this number becomes smaller. Yeah, this number becomes smaller. Therefore, the maximum value you can have is increased. So this is what will happen. This is for the off resonant drive. So this is when you have not off resonant drive, but then you increase you increase your power, your microwave power. You have a higher value and you have a shorter periodicity. Okay. Now, I want you to notice one thing. Say for the same amount, since we are fixing our drive period, okay? And here, of course, we're using the pi post time. But let's say we are, just for discussion's sake, let's say we're here. This is our post duration, okay? You see that there are two factors that boost this up. One is that your periodicity is shorter, right? So even with the same maximum, with the shorter periodicity, this still goes up, right? So that's one factor. But there's also another factor, that is this increase of maximum probability also pull this up from what is supposed to be up, and this two increasing factor does not scale equally with power. Understand? They do not scale equally with power. Okay? So what I'm trying to say is this unequal scaling end up lead to the saturation. Okay? It end up lead to the saturation of your spectrum, of your spectral density. Okay? It can't, I mean, there's really nowhere to go when you drive it up. Before you drive this down, of course, because this is, of course, Rabi oscillation, right? So if you for the same amount of time, if you continue to increase the power, this will become smaller, and then the pi post time, which give you the maximum, could give you a minimum, right? So before that happen, this will increase, and this point will stay at the maximum. But the unequal scaling will make this increase kind of faster with small detuning and small with large detuning. Okay? Because of this unequal scaling with time, with the periodicity, and with the height. So the net effect is when you have two detuning, this will increase more than this. They are not scaled equally. So this nonlinear scaling end up give you a broader shape in your spectrum. If this will be a linear scaling, for example, I have a Gaussian, right? If this will be a linear scaling, this goes up, everything goes up by the same amount. Your width. So for example, if my just to explain what is the linear scaling. If my spectrum width, if my spectrum is like this, okay? Then this goes like this, right? So say if this is my spectrum, and if I increase my drive strength and everything, no matter which detuning, they all increase by the same amount, right? This is called the same scaling. a linear scaling. Then this goes up, this goes up, this goes up, this goes up. Everything goes up by the same amount. Your width, your halfway width, this is a really bad drawing. But your full width half maximum, your width will remain the same. Okay, if you have linear scaling for all the detuned frequency. But if you have a nonlinear scaling for your detuned frequency, then you will have this saturation, this kind of saturation effect. And that is the physical cause for power broadening. Okay? So just remember, if your purpose is to determine some kind of, I don't know, frequency center or something, you probably want to use as less power as possible, right? Because you want to avoid this power broadening problem. Okay? That brings us to the second issue, transient broadening. All right.
Sorry, what does, for the red XY axis, what does the Y axis?
Y-axis P.
Probability of seeing the excited state. And
Yeah.
the left is the OMPR signal.
Yes.
But does it have a max?
Of course, 100%.
Max is the 100% of what and what? What over what? The 1 equals
1 equals.
everything.
Okay, let me just use the ensemble interpretation. So there are two interpretations of quantum mechanics, and it's called the Copenhagen interpretation. Okay, and they are really just two sides of the same coin. But let me just explain this with ensemble interpretation. So say you have a lot of identical MV center. Okay, and when you offer a pulse, initially they are all prepared in the ground state, and you offer a pulse. What will happen if you offer a pulse that is this long? Okay, that is this long, and then no detuning, and you look. After you offer the pulse, you look. You use some kind of method to check the energy of the system or to check the population of the system. Okay, so say you can do that. There's a way for you to examine how much of them are in the excited state. Okay, then you will find that all of them, all 1 million MV centers will be in the excited state. Okay, because you have 100%. Okay, but say if you change your pulse duration to by half, so you have this pi over 2 pulse duration. Okay, and that's basically the half of this value. You do the same thing. After the pulse, you check again and see how many are in the excited state. You'll find that 500,000. You'll find a 500,000 MV center, and they are randomly distributed. 500,000 will be in the excited state, and the other half are not moving at all. They are just in the ground state.
Okay, so this is the theoretical one, but for OMPR,
yeah,
our result is not close to 1, right? So 0.001 or
yeah,
around that.
The maximum value is 1. The reading that you read, that was just some kind of, you need to scale your signal, right? It's like if we give an exam and the maximum score is 5, right? And you scored like 4.9. Is that a low score or a high score? That's a high score, right? Because if we normalize our score to 100%, then 4.9 is like 99%. Okay, so what you get is some kind of a ratio. ODMR is PL microwave on, no, sorry, microwave off, PL microwave on over PL microwave off. Okay, so that's in one of the lab objective. That actually, that's the one of the first, in the first lab, in lab 1, you're asked to do this.
Yeah, but
Okay, this is a ratio.
okay. But
And this ratio has a maximum value. And that maximum value represent, if you normalize it, it will represent 100%. That value, you take that value, okay? And of course, you need to remove the background. So say if your oscillation is like this, right? And this is, for example, 0.3, okay? I'm just making it up. And this is 0.7, yeah? Then what you need to do is you need to see this as, this is 50%, and this is 0%, and this is 100%. So you need to shift your signal, and you need to scale it to normalize it so that the dip and the peak and the center match this 3 number.
Yes, but how the ratio to normalize is always determined by the system, right?
Yes.
You can maybe you can, but it's very hard to calculate like what's the maximum.
Right. Yeah, of course. And
because all
and
the noise, all the
and if my optical alignment is a little bit off, you probably don't get 0.7. You get 0.07 even, and this could be 0.003. Okay, so this absolute value changes, but you need to understand what it means. The peak means 100%. The dip means 0% for the excited state, and you just need to shift the thing, the entire thing, and then you shift it, you offset it, and you scale it so that it's this experimental data you have physical interpretation. And you do this for every data you take.
So I'm just saying that what we observe is because I try to ask it because there's a max value here, right? For Paul broadening, there's 100%, and to increase the microwave figure, it broadens. But for the ODMR, we can have other factors that make it, maybe we align it better, but it increase even if
when you are only changing, if you already normalize your signal, okay? Of course, so how do you normalize your signal? Yes, that's another issue. But you do it once, you calibrate once. So you try to find your zero detuning, okay? And whatever the peak signal is for you, that is your maximum. So that corresponds to 100%. And whatever shift, so this line here is supposed to be 50%. So whatever that is, you shift it and you take this. So there are 2 values. So this is 0. So they are the center position, and they are this gap. I'm sorry, this amplitude. All right. So there are 2 numbers. So under the proper condition, which is this, you normalize the peak value to 100%. So maybe in your turn, 0.07 is 100%. Okay. So after you've done that, then the only thing you do next is to change your frequency, right? Then you'll get this, because this is 100%, so you naturally get this, right? You don't need to normalize for other frequencies, yeah? And then the next thing you do, the only thing you do next is to increase the power, okay? So say if you didn't use the full power, you use, say, 0.5, all right? You use 0.5, and then you find a certain pulse duration, it gives you the maximum, okay? Now, there are still some room for increasing power, right? So you increase it, you increase nothing but the power. You don't change the pulse duration, you don't change optical alignment, you don't change anything. You just increase the power duration. Sorry, the microwave power amplitude. Then you will find that this thing gets broader. And that's the power broadening I'm talking about. Okay? So of course, if you change a lot of things at the same time, you cannot make sense out of your data because you don't know what does the change correspond to. In the experiment, you always make only one change at a time. And that will allow you to know what's the corresponding change this parameter make for the system. All right? Okay. Let me continue.
Sorry.
Yeah. Let's shoot. Let me just finish this transient time broadening. Then we will take a break. All right, so say you want to work with low power because you're aware of this power broadening issue, right? But what does that mean? If you want to work with low power, so you go from this red line to the black line. You work with lower power, so it goes down, right? Then it will require you to drive it longer. Yeah, it will require you to drive longer to reach the maximum. Yeah, yes. It will take longer time to drive to the maximum. Okay, so that means.
But it's the maximum of that power.
Right. Yes, exactly. Right. Now remember this condition. It's always a function. Is a two variable function. It depends on. Actually, it's a three variable function. It depends what your amplitude, your probability depends on your detuning, the length of your pulse duration, and also your pulse power. So there are three things. So whenever you fixed one of them, two of them, and you want to get to the maximum, you need to search for the third parameter to get to the maximum. Okay. So say you use a low power, you use a small power, right? You use a small power, and that means you will need to increase your tau to get to the max, to get to 100% of zero detuning, right? Now, what will happen to your line shape? It doesn't say here. It doesn't say in this formula. Okay, so this is an extra thing I want to tell you. So say the original, okay? The original is like this. Now you increase your, so this is, say, this long, okay? Now you make it maybe this long, right? What will happen to your? Does it go here? Or does it go here? It doesn't say in this formula. Right? because here I'm setting the tau to a new value, to a new chi, so that this is satisfied, right? Right. So I fix my pulse duration, and for the rest, it doesn't the tau is not involved in the rest of the formula. Simon, what do you think? One, A or B? Phoenix say A, right?
If you decrease the power.
If I decrease the power in order to reach the maximum, because I want to work with as much signal as I can, right?
Yeah.
Then I certainly want to increase my duration so that it will reach. See?
I'm also thinking, because if you have to charge it for a longer time, right, to reach it.
Yeah.
So that will also cause it to, because the lifetime is not of the. I think it will cause like they will go out of sync the photons. I think it will be B.
You will not go out of sync with photon because the detuning, it is the frequency that determine whether you are in sync with the drive or not in sync with the drive. Now I'm talking about the envelope.
Yeah, but I guess the envelope will also broaden because the physical time it takes to charge it, if you have lower intensity, will be longer, right?
Yeah.
And if you do even if you are completely in tune, you will see that after a certain amount of time, you will lose the oscillation.
That's another issue. The loss of oscillation is not.
But like when we did the lab, and even if you have a
right,
frequency,
that is due to
after not very long time, you would still lose oscillation.
Yeah, that's called the coherence.
Yeah.
Okay,
so
we will not include that in our discussion for now. Otherwise,
okay,
we will not be able to.
That we don't have the
yeah, let's just stay with this very simple model, Rabi model.
Okay.
In the Rabi model, there's no decoherence. Okay.
Okay.
Okay. I'm not asking you for real world situation. I'm asking you for what you think logically what might happen.
I see.
What do you think? Don't use your computer to look for answers.
No. I just check it from a lab signal to remember.
Okay.
It will have more. The center will have more peaks. That's what we get.
And you probably puzzled at that time what that is. Yes. But so it's kind of good to have some experience first, and then when it comes to this, you say, "Oh, now it makes sense," right? Yeah. Instead of like, "What is this good for?"
but I still know how does that formula transform to our
result. That you need to spend something to think about. Yeah. Just give me an answer, please. We are running out of time. A or B?
B.
A or B? A. Okay. Great. Okay. There's no bonus credit for this. All right. The answer is A. Okay. And let me tell you why. Because there's one thing that we always forget. That we don't have an infinitely long drive, right? For a truly sinusoidal drive, it has to be infinitely long. If you put an envelope function on the sinusoidal function, so say if you put an envelope function, so this is this, okay? And if you put an envelope function, let me just say now, if I put a Gaussian function, yeah? Okay. So if this is not a top half pulse, this is a Gaussian, it's the same thing, okay? If we put this, then we no longer have a sinusoidal function, because a sinusoidal function is a function that lasts forever, right? if it lasts only for a finite time, you will have an additional term in your function, right? And the result is that the spectral content of the pulse, So let me write. So this is omega. Okay, the spectral content of your pulse will be determined by your pulse duration. Okay, and this is called Fourier transform. Okay, so if this is ET, this will be E omega. Okay, the Fourier transform. The spectral component or the spectral content of the pulse is not a single frequency but multiple frequency. Okay, and the shorter your pulse, the more component you have. That's not hard to imagine because, say, if you have this pulse and you truncate it with like by this much, right? You truncate it. How many? So this is your real pulse, okay? How many Fourier components does it take? Each Fourier component is infinitely long. Wave, right? How many components does it take to fit? To get a fitting to such a waveform? A lot, right? Yeah. A lot. But if you have a longer pulse, okay, so say this much, you truncate it. It doesn't take too many, right? Because this is very similar to this.
Basically, Fourier transform time resolution.
Yes, yes. Okay, so that means the shorter your pulse, the purity of your frequency becomes worse. The purity, okay? How defined your frequency is becomes worse. Okay, the spectral content of that becomes worse. That means if my resonance, if my true resonance is here, and that resonance is super sharp because the lifetime is long, okay? So there's this energy time uncertainty. Okay, you have heard of position momentum uncertainty, right? Okay, there's also energy time uncertainty, and both originate from the Fourier transform. Okay, so if you have a certain lifetime in your excited state, and if you stay there for a while, you decay. Then that decay time is translated to the uncertainty of your excited state energy position with respect to the ground state energy. Okay, so here, like normally we draw this, but this is a picture when the atom does not decay. If the atom does decay, then this actually is not a line. This is something with the width. Okay, and we call this the natural line width. And if the decay time is long, then the natural line width is short. They are inversely proportional to each other. Okay, so this is natural line width. Okay, usually it is very, 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 very sharp, like say kilohertz, even 100 hertz. And the frequency the microwave frequency that you use is gigahertz. See, it's like, and the width that you usually have is like megahertz. So this is very sharp. Okay, now if you have if you have if you have, okay, let me try to correspond. Let me try to correspond. 1. Ooh, man. The short almost get destroyed. Okay. All right. So say this is okay, this is A and this is B. Okay. So you see that this is A and this is B. Yeah? Now, if I use this drive, A, then see, when I scan the central frequency, right? So this detuning is defined as omega minus how far away you are from the natural frequency, from the resonant frequency of the system. So say if I choose my drive to be here, right? Pretty far away. In principle, I cannot excite it. But that is for a single frequency component drive. If I have a multi-component drive, then actually I have so many, such a fat tail that, you know, I can still have a little bit touch. I can still have a little bit of my frequency component, my frequency component touching the resonance, the QB resonance, and this will give me a little drive, a little value, a little excitation. If I move this in, right, I have more, right? The frequency that matches with the resonance has a higher intensity, higher spectral intensity. Therefore, I will have a more population. I will drive more population. So that's like this. Okay. So basically, if this is really narrow, what you trace out is the shape of your spectral, your spectral profile, the spectral profile of your pulse. Okay. So this is 2 pi T1. Okay. If instead we use a longer one, you can imagine that the resonance spectrum, the Rabi spectrum that I get is going to be small, narrower. Yeah? So this central frequency, this is fixed by my pulse duration. This frequency component, the range of frequency that I have in my pulse, is fixed by my, not by my microwave drive, but by my pulse duration. Okay, but the center frequency, the carrier, the so-called carrier frequency.
So this means inside your burst, you already generate a lot of frequency.
Yes.
It's like E-wave or something.
This is called the carrier frequency. Okay, this carrier frequency is controlled by our microwave drive. And when we do the scan, we scan the carrier frequency. So you see, the drive, the microwave have this envelope in its spectral content. So when the central frequency, the carrier frequency is scanned, the whole envelope move with it. Yeah? So when you have the central frequency matching with the qubit resonance, this entire profile that you see in the excitation spectrum of your qubit mimics the shape of the spectral content of your pulse. Okay? So this width, you see this width gets broader when you use a shorter pulse. When you use a shorter pulse. And this is called the transit time broadening. Transit time broadening. Okay? This is called a transit time broadening. Yep. All right. So with that, I want to just take a quick break, 5 minutes, and I just want to say that they are the spectral width that you see in your qubit are determined by 2 vectors. Okay. Not a natural line width, because the natural line width is super short. It is dominated by 2 vectors. One is the transit time broadening, or the transit time, the pulse duration, and the other is the power broadening. Okay. By the power and the duration. All right. So this is a special, important thing to note when we want to discuss, because why do we care about the line width? Because we want to determine the resonance frequency of our qubit system, right? Everything you want to do with quantum information processing, you want to do it most of the time at the resonant frequency. Okay? For example, the pi pulse, the pi/2 pulse, like those pulses need to be done at a resonance frequency. Most applications, like.
Can I say why that's the transit time broadening is not appearing on the formula, the red marker, is because we neglect the time domain in this analysis.
No, simply because when we solve this equation, for the sake of simplicity, we assume that the time just runs on forever. The microwave drive is present for all time. Okay. It is just.
Or I can say
the model.
If that we have to solve this in Fourier transform all of it into time domain, so we can see it. Because this only contains frequency domain information.
No, this is a time domain formula. This is a time domain formula. And if we have added, you see, this is a solution from the Schrödinger equation. Have you ever solved a Schrödinger equation? If you have, you know how difficult it is. Therefore, to simplify the calculation, we do not add the pulse envelope. We just say, oh, this time runs from 0. What we do as an alternative, we say this solution is good from 0 to tau. Okay, so this is good from 0 to tau when my pulse is on. Okay, when my pulse is off, then the frequency, the CG and C just stay the same as the last value. Remember, if you were not here last week, right? But if you have watched the video, you will see that I said that everything here equal to CG tau, CE tau. They do not change because there's no interaction. And everything before the pulse, so this 0 times 0 is defined by the pulse. Everything before the pulse is equal to CG0 and CE0. Okay. So that's how we resolve this issue of not including the pulse shape in the Rabi model. We just would say, oh, this is good for this during this time, during this interval. Okay? And if you want to know, so for example, if you want to say no, how would the pulse envelope change the behavior of your system? You would need to do that with simulation.
Or I can say because it is a pulse with driving frequency. So I like discrete Fourier transform into 100 solution, and 100 solution will have 100 frequency with
Yes.
amplitude and
Right.
putting it in the red equation, and we can get it.
Yes. Right. Yeah, you can decompose, you can Fourier transform your pulse and make them into like a single frequency component and then add all of them together. You can do that too. Okay? Cool? All right. Yes. Although I still have to say that this is only good for top hat function, top hat envelope. So
What's top hat now again?
top hat means this, Heaviside.
Okay.
Heaviside. Have you heard of Heaviside?
Heaviside is like
Yeah, yes.
Heaviside is this?
Yeah.
I thought this is called step function.
Yeah, and top hat is just that it goes down again. Yeah, now it's top hat.
So this is called heavy head. Heavy head. Anyway, doesn't matter. I call it top. I call it top head because it's a head.
Yeah, I see.
Okay, top head. All right, let's take a break. And I hope that we will be able to cover more. All right, cool. Okay, let's see if I can rush the rest of the lecture in the next hour. All right.
I guess this this power basically we don't change that in the lab normally, right?
Right.
It's the amplitude. I guess it's the amplitude that we just set to
1
volt, right?
Yeah.
I guess technically you could try decreasing this one to see.
Yeah. So you already have the maximum power broadening. In other words.
Yeah. I mean, I guess it would be desirable to try to lower it and see if you could get.
Yeah, and that's one of the regular objective, to scan the spectrum as a function of your drive. Remember 0.05 volt. We go from there all the way to 1 volt. If you
is that part of which lab? But that's not lab oscillation. It's a different lab. Yeah, it's lab 3.
Lab 3 is Rabi oscillation.
Oh wait, which is lab 4? Is then
lab 4 is Ramsey.
Oh, it's Ramsey, right?
Yeah.
But Ramsey is also a bit. It's related to this, I would say.
Mm-hmm.
But yeah, it's not exactly the same.
That's what I will try.
Yeah.
I'm trying to cover today.
But if you don't have time, you do this next week. Or?
Oh gosh, I cannot, because we already do 2 spin lectures in a row.
Oh,
Next
right,
week we have to do
optics.
optics. Yeah, like I said in the beginning of the lecture, they are just simply too much material to cover in this course, in this one course. This is basically 3 courses packed.
Can't you just extend the credits so you get more time?
What?
Like, can't you ask the university to change it to a 5-credit course and have 2 lectures every week? 1 3-hour lecture and then.
I cannot. I have trouble. Originally, this is a.
This originally is a 100.
They already increased it this originally I think this is a 2 credit course.
Okay,
And-
so you
and-
got them
and-
to free.
I basically work for free. The department changed this to a 3 credit course this semester, and I'm afraid that's the most they can do.
Last semester it was only 2 credits.
Yeah,
That's crazy.
yeah, I know. And I asked them if I asked them if this can be changed to a 4 credit course. They said
Yeah.
no. They said no, because all the experiment course, all the lab course is 2 credit at
But
most.
this is also a theory course. That's the thing.
Yeah, this is a very special course, but they don't care.
Because I guess if you assume that the students know this beforehand, then you could argue it's a 2 credit course. But now, of course, the student, if you
See. So what I'm trying to do is I'm trying to working with this framework, working with this much time, and then using recording, using all kinds of tool to, like for example, I align the the optics for you guys to make it possible to finish this within. But this is not how you normally would do it.
No.
Normally, people will spend like 6 hours there and try to
Yeah, of
do the
course, people
alignment
do
and
alignment,
struggle,
that's a bit of a fun
and
purpose also.
it's a lot of work. Okay, so we're working with what we have. Yes, what do you need?
May I remove this?
Yes.
Plug in the.
Yeah, but this is to help you see. This is to help you see the different fringes.
That is in the
Oh,
nanotech.
So do I
So-
see it using?
You can use this. This is aligned. This is if you want to scan. For example, if you already see the fringes
Yeah.
and you want to find the maximum, right? Then you remove this and then you scan it and then you will see the oscillation, and then if the oscillation reaches the maximum, the envelope reach your maximum, you know that position is the perfect overlap. So when you are ready to do that, you remove it and then you use this to monitor the trace. But if you don't have fringes, then this won't help you. Huh?
You mean the fringes with the LED or the single photon?
Okay, so the alignment process is that you first do this with the alignment laser,
Yeah.
right? So have you done that?
Yeah.
Okay,
I
and you
have-
can see fringes, right?
Yeah.
okay.
I see fringes or
And
LED.
and if you also see fringes with the LED
Yeah.
on the camera.
No, I just using a screen.
Can you see fringe on the LED?
Yeah.
You can see. Okay, perfect. Then at this point you can take this out and then
Okay.
use this to lock down the overlap position.
Okay.
Yeah.
Sure.
Yeah, and if you want to put back, it's not too hard. You just need to put the camera to the full view,
Okay.
and then rotate this. Yeah, you just pull it out. It do not remove
I
the
see.
base.
Okay. Sure.
Okay.
Thank you.
All right. Do everybody has a drink and use restroom?
We didn't do that. We just set a computer number. So basically, what inside, we just change your program. How many lanes? Something like this. Yes. Oh, so this is just postcode. You can set it. You can click one here. I didn't have the screenshot, but if you click another point, you can set the how high the width is. So basically that is just change number and click change number.
All right, so let's come back. So in principle, like I said, to determine your resonance frequency, okay, so let me just draw this. To determine your resonance frequency, you want this to be as sharp as possible, right? So in principle, you will want to use not a high power short pulse, but you want to go for a low power long pulse. Yes? Okay. When we have a low power long pulse, we minimize the power broadening, and we minimize the transit time broadening, and life is perfect. Yes? Who will believe that? Who believes that life is perfect? Nature always has a way to screw us. Okay. So let's see what happened here. What happened? So in principle, with this, you should have a very slow oscillated. You have a very slow oscillating signal. So this is PE. This is time. Right? And sorry. And then it goes like this. It's very slow oscillating. Yes? And let me just say here, this is 1 microsecond. That is 1,000 nanosecond. And this will be 3 microsecond, right? In principle, we would love to see this, and this will potentially give us a very narrow spectrum, and life is great. But in real life, in the lab, do you see this? No. What you see is that when you do this, this kind of dies out. Almost around 500. Okay? Okay. And if you use a short pulse, like here, maybe I should change the color. Otherwise, you get confused. Okay? This is that, and this is this. Okay? Now, if we use a short pulse, what we see is right? This is what you see in the lab.
Yeah.
So it's nothing like the Rabi model that we talk about. Well, it's maybe a little similar, but it's not exactly the same, right? Most importantly, it prevents us to use a very long pulse to reach a nanoline width. Yep. So what's the reason for this thing? It seems that it will die, the oscillation will die out, and this will land to the middle. Well, let's take a closer look. Let's take a closer look at this. Okay. Let's take a closer look at Rabi oscillation. A closer look. Now, how do we understand Rabi oscillation? Is it basically two bucket? Okay, I have some MV in the ground state bucket and nothing in the excited state bucket. And if when I offer a drive, right, when I offer an excitation, I move them to the excited state bucket. And this start to fill up. Okay, so far that is consistent with the picture of our excitation, right? Okay. Now, remember last time we also said that besides excitation, there's also stimulated emission. So the drive can also, if initially you put your bucket, your MV center in the excited state bucket, and you turn on the drive, this can also happen. The same drive that excite the MV from the ground state to the excited state can also de-excited or stimulated, make it perform stimulated emission, and they will move them to the ground state. Okay. So with this picture, I would say the if we work this picture that we have two buckets and then you have this Mr. Microwave. He's working as a mediator, and he just do this. Take MV or marbles from this bucket to the other bucket, and take marble from this bucket to this bucket, right? Initially, you will have, if you have a full bucket of MV here, or marble, let's just use marble. If you have a full bucket of marble and an empty bucket, then initially this will get filled and this will go down, right? But when there are more marbles in the empty bucket, some of them will get put back to the ground state bucket. So eventually, you can imagine that you will reach a dynamical equilibrium. And that in that dynamical equilibrium, nothing changed. Nothing changed. You have the same amount of marbles that are moved out of this ground state bucket as the marble that are moved into the ground state bucket, right? Nothing changes. Nothing changes. This is called the dynamical equilibrium. And this dynamical equilibrium typically reach at 50%. Yeah? So if the coupling strength is the same, so say chi and chi, if the coupling strength is the same, then you will have no change in your marble number when they are the same, when they are about the same. PE is 50%. I'm using P, this is probability, but I'm using this to represent the number of marbles, and PG is 50%. Yeah? This is what classical physics tells us. And this is described. Such a dynamical, the 50% dynamical equilibrium is derived from the Ray equation. Okay, it's derived from the Ray equation, which I will just give you here. This is the Ray equation. The change of the PE will depends on how much you have in PG. If you have something in PG, then you can have an increase, okay? A positive increase in PE because you shuffle marbles from PG to PE, right? But if you have marbles in the excited state bucket, you can also lose it through stimulated emission. Okay? So this is the Ray equation. And the same goes with the other bucket. PE minus PG. Okay? And if you know how to solve differential equations, you will the final solution is this. Okay? What this shows is, so say if my initial value is, I have everything in PG, okay? I have 100% of my MV or my movable in PG. Then you will have an exponential decay, and then you will finally this term will die out, and then you will vote at 50%. So that's one half. No, this is Ray equation.
So classical.
This is a classical. This is a classical picture of it. So this is PG. This is PE. Okay. So if our excitation is just this simple, if our excitation is just this simple, just moving marbles from one bucket to the other, then this is what we expect to see. An exponential change, and then it will stuck at 50% of dynamical equilibrium. Yep. But that's not what we see, right? What we see in our experience, at least for the first few cycle oscillations, we see that it does reach a minimum, a zero, as they start with, and it does reach 100%. Okay, so what happened? What is going on? I'm not like previously. I gave you the Rabi model formula because that is the simplest way to understand the dependence in its spectrum. Okay, the power broadening, the transient, all that. Okay, but now I want to talk about physics. Okay, so let's forget about the solution that we just have. Okay, so right now the question is, why does it go over this 50% line? shouldn't it stop there? I mean, according to the Ray equation, it should stop there, right? Why does it go over?
Because there's probability of it happening.
No. Like I said, there's probability for it to be moved to the other bucket. If these are the two processes that are involved, then this is what is going to happen according to the Ray equation. Okay.
We expect quantum effect, like it's a superposition, so it's not as simple as it just goes from one to the other.
Okay. Yeah, you're correct. The fact that we see that it exceeds the 50%, the classical 50% limit. Okay, let me just write this down. This is the classical limit. The reason that we see that it exceeds the classical limit is exactly because quantum interference. Okay, so let me draw this again. G, E. Okay. Let me. Okay. All right. And this is kind of fun. I'm sure you won't hear this anywhere else. I'm pretty sure. So this is kind of fun. First of all, when we have a dominating, we have two processes, right? One is this, and the other is this, right? When we have a lot of population in the ground state to begin with, this process will dominate over the other process. That is understandable, right? But when they are now also 50% of the population in the excited state, when we reach T1, when we reach this point where the population are the same in both cases, for classically you will reach equilibrium, right? But quantum mechanically it is not so. These two processes, they will interfere. And depending on the phase, if you have a positive phase, they will interfere. And the excitation will dominate due to interference. Okay, if they have the positive phase. So this becomes a bigger lump. Okay, so that's from T1 to T2. If they at this point they interfere, and if the two processes have the same, so this is probability amplitude, the excitation. When in quantum mechanical they are called probability amplitude, right? And which is distinct from this probability. Probability does not have phase, but probability amplitude does. Okay, probability is a real number, but probability amplitude is a complex number. Okay, so this process can interfere, and when they interfere, and their phase is somehow if their phase is the same, then they interfere constructively, and it goes up. But when we go from here to when we go down, right? Here we have 100% at the excited state. Here we have, so this is 0, T0. T0, we have everything in the ground state, right? And then we reach 50%, and then we are here, okay? Now, we are at T2, right? And like before, there are two processes, but because we have 0 population in the ground state, so the excitation process, like there's no effect. There's only stimulated emission, right? So stimulated emission will dominate until they reach also again a 50% population. Let me just write it here. Until they reach 50% again. Okay? And at this point, guess what? The two processes interfere again, but this time, the phase is opposite. They don't have the same phase. The phase is opposite. Okay? And the result is the stimulated emission dominates. And it goes below the classical limit. Okay? So what I'm trying to say is going over the classical limit, these are due to quantum interference. Yeah? And if you have the formula I gave you, you will see that in the probability amplitude, that the probability amplitude oscillate at the period of so this time is 2 pi over omega, right? This is a cosine square, right? This is a probability, yeah? But for the probability amplitude, you oscillate with cosine, not the cosine square. Okay? So from the probability amplitude, if you track the probability amplitude, you will see that, let me just draw here, not on forget about the vertical axis. The probability of amplitude goes like this. One is cosine, and the other one is sine. Oh, sorry. Okay. So one probability is cosine, and the other is sine. You see, the two probabilities are in phase. Which screen? See, they are in phase. They are both positive. Before they're positive, the sign is the same. Before this time. So this gives constructive interference. But here, the sign is different. One is positive and the other is negative, right? So that's destructive interference. And in the next cycle, they are both negative. The sign is, again, the same. So constructive interference. And in the next cycle, the signs are opposite, destructive interaction, destructive interference. Okay? Therefore, going over this 50% classical limit is a quantum interference effect. So Rabi oscillation is a quantum interference effect. It's a quantum effect. Okay? All right. So formally, this can be understood using, no, I'm not going to teach you density matrix, but something else, something more useful. This is actually derived from density matrix, but this is much useful than density matrix. So like I said, so since this 50% over or under is due to the quantum effect, the fact that we are seeing an oscillation that dies out and converged to the 50%. This shows that we're transitioning from the quantum domain to the classical domain. Okay? This is the so-called quantum to classical transition. Okay? And this contains the most profound mystery of quantum mechanics that has not been solved yet. So this is still the frontier of physics research, the quantum to classical transition. But here we're already seeing it. From this very simple Rabi oscillation, we witness the quantum to classical transition. Okay? Now, the Rabi model was developed under the framework of Schrödinger equation. And Schrödinger equation is a fully quantum model. Is a fully quantum theory. So in order to describe this quantum to classical transition, this envelope, okay, you cannot just add an exponential to this. It doesn't work. Okay, in order to describe this, we need something a little different. We need a more general framework. Okay, and that is called the optical Bloch equation. Okay, that's called the optical Bloch equation. Derivation of the optical Bloch equation is rather complex, but I have upload my note to the eLearn. So if you're interested, you can take a look. But here I will just give you the result. Okay. All right. Okay, so this is the optical block equation. You see, it's really complex compared to Schrodinger equation, right? Well, for one, Schrodinger equation is an equation of two, a set of two equations. This is a set of three equations. Okay, and there are so many more terms. Okay, so this is rather complex. So, but why do you want to use it? Because, by the way, this form, so far, this is derived from the Schrodinger equation. This is just another form of the Schrodinger equation. And the reason we cast it into this way is because U, V, and W have geometric interpretation, which I will discuss later in our lectures about on block sphere. Okay. Second, they are real numbers, so they can be measured. Schrodinger equation, you have CG and CE, right? They are complex numbers, they cannot be measured. But these are real numbers, they can be directly measured in one of our lab called quantum tomography. Okay, so these are actually very useful. And this is just another form, like here up to this. This is just another form of Schrodinger equation. So this interference, a quantum interference that makes this jump go over the classical limit, it's also shown here. It is less obvious in Schrodinger equation, but it is kind of clear from equation that we discussed here. I want you I'm not gonna go into the detail of optical block equation or explain what is block sphere, but what I want you to pay attention is this W. This W is defined as the population difference. Okay? This W is defined as the population difference. And if you like, you can also cast this into a form of W. So define W as PG minus PE, just like we did here. Okay? And you'll find the classical rate equation is actually this. Okay? And wait. Right. Okay. So this is the classical rate equation. This is the quantum rate equation, if you prefer. This is the quantum rate equation. Yeah? And the main difference is that you see that this does not depend on the population, but it's depending on the coherence, U and V. So UV contains the phase of information of the probability amplitude. Okay, this is kind of a strange combination, but you can see that this is complex number. its component is complex number, versus for W, the component are real numbers, right? So U and V actually characterize the coherence of the system. And when U and V dies out, okay, sorry. Let me say it again. When there is coherence, then you have extra contribution other than this classical term. You have extra contribution to the ray equation, and this is the quantum interference I'm talking about. Okay, but what about that term? Well, that term is responsible for the decay. It corresponds to the decay of the ray equation. So after deriving the optical block equation from the Schrödinger equation, if this is identical to the Schrödinger equation, it cannot give us more information. In order to describe this kind of decay, we will have to add this phenomenological term. These are not derived, but just added by hand, and they are called the phenomenological terms. And this describes the decay of coherence at the time scale of T2. And this is the decay of the population difference at the time scale of T1. Okay? Actually, T. This part is the classical part. This is the classical part. You see that they have basically the same form. No, sorry. My bad. Let me take it back. They don't have the same form. This is related to the drive, and this is not related to the drive, so they are not the same form. Okay? The dependence, the classical coupling, that actually comes through the coherence dependence on the omega. Sorry. So this is much more complicated. I'm sorry. So if I just have W, I have no this term, right? My U and V just depends on W, then this will depend on W. Okay, and then you can kind of recover the classical ray equation. Okay, so rather this part is the classical part. This is the classical part. Okay, and the reason we can have more than 50% exceed the classical limit is because of this. These are the quantum interference. These are the quantum part. Okay, and both the quantum and the classical all included in the coupling. Okay. And now, in order to describe, and you can see that with the decay of my coherence, with the loss of my coherence, which we typically call decoherence. Okay. T2, decoherence time. With the decay of my U, the effect of the quantum goes away. All right, and you're left with the classical, and so your drive to 50%. Okay, so if you don't have this, you will be driving to the 50%. Okay, and if you add this will further give you so for a long time, it will further give you a decay down to the ground state. PE equal to 0. Okay, so this is called decoherence, and this is called relaxation or thermalization or damping or dissipation. Okay, there are a lot of names for it, but they basically all mean the same thing. They kind of bring this down to the ground state. Actually, thermalization bring it to 50%. But anyway, that's a detail. Okay, so this is the optical Bloch equation, and this is what you need to describe this decay in the Rabi oscillation. Okay, there is, like I said earlier, that one of the appealing reason that we would like to use optical Bloch equation for real-world application is because in addition to the ability to describe decoherence and relaxation, it also has a very nice geometric interpretation. Okay, and this interpretation mimic the equation in NMR, nuclear magnetic resonance, because in nuclear magnetic resonance, that equation is originally called Bloch equation. So, and because the similarity between this and that one, this is called optical Bloch equation. That's how the name comes in. Okay, so here I'm gonna just write down this without much explanation. We will come back to this when we talk about Bloch equation. But you can define a spin vector with u, v, and w as the 3 coordinate, and you can define an effective magnetic field. This is not a magnetic field, but it just mimic the role of magnetic field in an MNR equation. So we call it effective magnetic field. Okay, so this is and this whole equation for this part. So if we only concern ourselves with this coherent part, okay, this can be cast into this form. Okay, so it's a quantum spin in an effective magnetic field. For NMR, the Bloch equation is the magnetic moment coupled with the real magnetic field. You see how similar they are? Okay. This is the magnetic moment. So if you add some kind of effective gyromagnetic ratio, then this can also be defined as a magnetic moment. Okay, it doesn't matter. What matters is this form, this vector, these 3D vectors possessed around this B field. Okay, so this is all very cool, but we will only discuss this later. These are decoherence. Shit, we were running out of time. What should we do? Ramsey. Oh man, I really want to finish Ramsey. If we don't finish Ramsey, we'll be in trouble because.
I don't know if it's optical lab, but because the spin lab is already further into.
Ramsey is the base of everything.
Yeah, so maybe we need to learn it before we do it more.
Yes, I think that's a good idea because Ramsey is the base of everything else. For the more advanced sequence, for one pulse, yes, that's Rabi. But for other things, everything else, you need to understand Ramsey. Okay, so I really would like to finish this. Plus, we don't have more time for spin lectures. Next week, we're gonna do optics. Let me see if I can really haste through this. Okay. I think I can do it. I think I can do it. Okay. All right. So let's come back to our resonance problem. Okay, you see, our problem was if we want to lock down our resonance frequency for the qubit, we need to make our pulse very long, right? But then this problem of decoherence stands in the way. That prevents us to make our pulse very long. Yeah, that's one thing. Second, there's also a stability issue, right? How long you want to be the pulse? 1 microsecond, 2 microsecond, 1 millisecond, 1 hour. Of course, the longer, the better, right? But there, soon you will run into problems with system stability. How stable is your microwave generator to generate a perfect sinusoidal wave without any phase jump for 2 hours? Yeah? You run into stability issues. And actually, it was for this exact practical reasons that Ramsey developed this thing called Ramsey interferometry. Okay? Simply because, at that time, because a long pulse is not feasible because of stability. The experimental apparatus cannot be stable for so long, at least not for the time required to resolve the natural line width. Okay, so Ramsey, think a lot. Ramsey is the last name. Think a lot about this problem, and he came up with an ingenious idea. Instead of using a very, very long pulse, one very long pulse, he used 2 pulses, and the 2 pulses can be short. It's just that the 2 pulses needs to be separated by the same amount of time. So if this is t, that's how long your pulse needs to be separated. Okay, so instead of one long pulse, you do 2 pulses, pop, pop, and they are separated. Okay, and how does this really work? And let me just tell you the result. So the result is with a regular pulse. So with one regular pulse like this, okay, you get a spectrum like this. But with 2 pulses, you get fringes. And these are called the Ramsey fringes. It kind of goes without saying that this is a quantum effect. Pretty obvious, right? Anything you see that is oscillating are likely quantum effect. Okay? So this is a quantum effect. And you notice that the width of the peak is now much, much narrower. Yes? It is now much, much narrower. So it is easier to pin down the central frequency, the resonance frequency.
But this is the result of the scan.
Yes.
Not the Fourier transform of the orange.
No. Okay. No.
frequency on the x-axis.
Hmm?
It's a frequency.
Right.
Yeah.
Yeah, the carrier frequency of your okay. Yeah. So you scan the carrier frequency, and this is your resonance. And see, it's very sharp. So it's easier to define the peak position. With a very flat top, it is kind of hard to. You need to have very, very dense sampling in order to really pin down the top point, right? But with this, you don't need a dense sampling because the difference between this and this is marginal in the Ramsey spectrum, but it is a lot. It is marginal in the Rabi spectrum, but it is a lot in the Ramsey spectrum. So you can easily tell that this is the resonance frequency, or this is close to the resonant frequency than the other one, right? Okay. By the way, this peak is here. All right. So how does it do this? Well, let's start with Mach-Zehnder interferometer. Mach-Zehnder interferometer. Because this helps us to understand the physics behind Ramsey interferometry, or Ramsey interferometer rather. So what is a Mach-Zehnder interferometer? Well, Mach-Zehnder interferometer meter is, we have actually talked about this in one of our first lectures, right? You have laser, you send through a beam splitter, it's split into two beams, and then you use mirror to recombine them to the next beam splitter, right? And there are two paths, 1, 2, and this interfere, okay? Or 1, 2. And this interfere, right? Remember, if we put a detector here, if the detector is bright here, the detector here is dark. Yeah, so let's just say dark, or dark here and bright here. They're always opposite, right? Okay, so the key of a Mach-Zehnder interferometer is these two beam splitters. Yes? These two beam splitters define two paths that can reach to, let me just call this the ground state detector, and this is called the excited state detector, okay? There are two paths that you can reach the excited state detector, and there are two paths you can reach the ground state detector using two beam splitters, okay? And so this is exactly what happened with Ramsey's sequence. Ramsey, this pulse, so this pulse usually that we use, the pulse that we use for Rabi, so this is Rabi. We usually use a pi pulse, right? A pi pulse puts you at the maximum. This is a pi pulse, puts you at the maximum. But for Ramsey, he used pi over 2 pulse. This puts you halfway. Okay? What does that mean to us is that the ground, if we start with the ground state, yeah, and then we come with an excitation, pi over 2, the pi over 2 pulse. This was split into two states, ground and excited. Yes? Right? And for this time that during the wait, because the microwave pulse amplitude is 0, okay? The microwave amplitude pulse is 0, so there's no interaction. The chi is 0, okay? So here, chi is 0. Here, chi is not 0. Here, chi is not 0, okay? So because there's no interaction, this just stays at its original state, okay? There's no change. Now, here, at this point, so let's call this this is time 0, this is time tau, okay? So let's call this tau. This is tau. This is time 0, this is tau. This is t, the separation between the two pulses. So you wait. So this is t, okay? And at this point, you offer another pi/2 pulse. What will happen? Sorry, this is not E, this is G. What will happen to the excited state? Does it get excited? Can it get excited more? It cannot, right? Can it go down? Yes. Which one does it take? Both. Both. Because pi/2 pulse give you half probability in the ground and half probability in the excited states. Okay? So this go both way. It can go to excited state, or it can go to ground state. Yeah?
Ground state can also.
Yes, the same goes with the ground state. Ground state can go to the ground state, and ground state can go to the excited state. Yeah? Therefore, you see, what is kind of cool is this analogy between the Mach-Zehnder interferometer and the Ramsey interferometer. For the excited state detector, there are two ways, there are two pathways you can go. One is through this, which I call GEE, okay? Let me just give the probability amplitude of this excitation path, GEE. And the other is this. Actually, GEEE. And this is GGGE, okay? And this is the excited state amplitude. There are two probability amplitude for the excitation path, and these two paths interfere with each other. Okay, so your probability amplitude is this. Oh, sorry. Your amplitude, which is your detection result, is this, and this will be GEEE G plus an interference term. Okay? So you see, this is exactly like the Ramsey. Sorry, like the Mach Zehnder. The Mach Zehnder has E equal to E1, E2, right? Remember, we talked about this, and E2 plus E star E2 star. And this is the interference. Okay? So this interference gives rise to these fringes. And the same goes with CG, so I'm not gonna write it out. Whatever PE has, PG is 1 minus PE, right? Because the probability needs to sum out to 1, okay? So if you can calculate PE, then that's sufficient, okay? Let's spend the rest of the time doing that in a rather fast speed. Because the reason I want to do, although this is not a calculus-based course, in the derivation, you will see a very important detail. And that will give you insights on how to do the experiment. Okay. Let me write down this. Okay. Let me just take this two paths, okay? Let me call it path 1 and path 2. Okay. In terms of time, this is 0, this is tau, this is t, this is, okay? Now, for the first part, we know how to do. Okay. For the first part, we know how to do. This is just the Rabi. This is just the Rabi pulse, right? Yeah. So if you have that equation I gave you, and you C, you start with CG equal to 1, CE equal to 0, because this is the ground state, this is time 0, right? Then you will see that the probability of going from here, G to G, is this probability this is let me write it. Let me just put this here. Need more space. I'm sorry. Okay. And 0 tau. Okay. This probability amplitude is this. C minus Okay. And this probability amplitude is this. Okay, so pretty straightforward, right? And our initial, by the way, our initial, so here our phase is 0, right? Because, oh, by the way, there's one very important detail in this. Because we are working with CG, we're working with interaction picture. CG. Okay, this is interaction picture, but the lab picture, the Schrödinger equation with the unperturbed Hamiltonian is called the lab picture. Okay, is CG G plus CE. Remember we talked about this a little bit earlier, right? There's a phase accumulated in the E, but we really don't care much about that phase. We really want to just know about how the probability amplitude change. So we can do a little math trick to the Schrödinger equation, and the resulting Schrödinger equation is called the interaction picture. Okay, so that's this. Yeah, all right. So in the interaction picture, here, the drive in this lab picture, the drive is this. Okay, but in the interaction picture, the drive also needs to be adjusted. I call it E prime. The drive is this. Okay, so it's as if the drive frequency is changed. Okay, so this is like the new drive frequency in the interaction picture. Okay. All right, so that's what I want to say. So here in the interaction picture, we have this, and our initial phase is 0. Okay, so there is no phase factor. There's no phase factor attached to our amplitude. Otherwise, there is this exponential minus I phi, right? Remember, if you use your computer to take the note, you will notice that last time we talked about this exponential I phi represent the absorption and the emission of a photon. We associate that with the raising and lowering operator of the photon field. Okay, this is absorbed. Okay, and so that's this amplitude. And here, because there's no interaction, the probability is 1. There's no change. There's not going to be any change in the probability amplitude. So that's 1. And now here there's another pulse. Okay, so here you need to pay attention. The pulse now is this, right? So here we have this. Here we start with 0. This is a very important detail. Here we start with 0, so you can use the Rabi solution. But here this is not 0. This is t. The starting point of the second pulse is capital T. Okay? So in order to conform this form into the Rabi solution, we need to make a little change, and that change is this. Let me just write this as new omega, okay? The new omega needs to, you need to reset it. You need to reset the time, right? So that this time is like starting from 0. And you run for a duration of tau, right? Because that is the presumption of our Rabi model. We start with a pulse at time 0 and we run it for tau. Here, if we want to apply the Rabi solution, we need to conform this field into the same form, okay? So this T prime needs to run from 0 to tau, okay? T prime, it goes from 0 to tau. So now, if we do this, then in order to make the equation stands, we need to add this number back, right? Okay? So this becomes cosine omega prime T prime minus T. Okay? This is super important. You won't find this in 90% of the textbook. It's all very confusing, but this is what comes down to it. There is a phase offset in the second pulse, and that's what make all the differences. There's a phase offset in the second pulse. Okay? And that offset is minus omega prime T, okay? And this minus omega prime T, of course, is just this in the original notation, right? And this, of course, is this, the detuning times T, capital T, okay? This is super crucial. So with this, under the new parameter, after we reparameterize the microwave drive, okay, let me just write this down. Prime. This is prime. After we reparameterize the microwave drive, we didn't change anything. We just changed the parameters. Okay, then we can use this, apply this, use Rabi model, with this T prime, and the solution, and the result is that we will get here exponential I tau prime C minus S. Oh, sorry, not S. Okay, and all right, and here you will have this. Very importantly, let me use green. Very importantly, you have a phase factor, and this is just S. Okay. All right. So these are the probability amplitude to go from here to here, from here to here, from here to here. So in order to go from here to here, you multiply the probability amplitude. Okay, that is just pretty simple. logic, right? The joint probability is all the probability times together, right? So this is like the joint probability amplitude. And when you do that, you just multiply all the probability amplitude together. By the way, this is also the core, the central idea of Feynman's path integral formalism. When you have different paths that start from the same starting point and arrive at the same final point, you just multiply the path, the probability amplitude of each segment of the path, and then you end up adding all this path together. Here we're doing pretty much the same thing as the path integral. Okay, so let me just write it down. So the first path is this term, I tau s, right? Times 1 times this. Yeah, that's the first path. This is path 1. I forgot to write. This is path 1. This is path 2. Okay, so this is path 1. There are 2 paths to reach the excited state. So we add the subsequent, the corresponding probability. The second path start with this. Exponential I tau 2 c minus this. Okay, so that's the first segment. The second segment is 1. The third segment is this, which is a very important term because it contains the phase. Okay, so that's this. This is path 2. If the phase is not here, if I'm missing this phase vector, right? Then you can imagine if I, for example, if I forget about the phase vector, if I just like kind of copy what we have here, then the entire equation will not have capital T, right? That means it doesn't matter how far your poles are separated, it will have no effect. Okay?
So the important thing is the phase.
Right. It will have no effect and it will not have oscillation. So the oscillation really comes from that phase.
So we need to make it not accurate purposefully.
Huh?
We need to make it not, the driving frequency need to be not at the real frequency purposefully.
Yes. Okay. Yeah, because if the phase is 0, if delta t is 0, then everything will be just as, right? And it's not hard to imagine because, well, let's not talk about that later. Because when we talk about Bloch sphere, it will become clear what happened if you are doing on resonance drive versus off resonance drive. And it's much easier to explain things there. All right, so let me just write down. I think this could be helpful, so I'm gonna just write it down. we can also wait for Phoenix.
Going to the bathroom.
Yeah, if you want to go, you can go. You can go now too. Yeah. Now you see why I want to use S and C, right? Because there are so many S and C in the equation now. If I write down, if I write all the cosine and sine, it will take forever. Okay. All right, so I think it's pretty clear. The first term, so there are two paths, right? The first term is the probability amplitude of path 1. Sorry, it's not the probability amplitude, the probability. So this whole thing, modulus square, that's this, okay? You can do this in your head. It's not too complicated. Here, this second term is this, right? So the probability of path 2, right? And now this is the cross term. Path 1 start times path 2 plus path 1 times path 2 start. Yeah? And this gives the interference that we talk about between the two paths, right? And it looks like a very complicated equation, but it's really not. Because if you notice, these are just two exponential functions, two conjugated exponential function add together, right? So let me just write it down for you. Minus delta t minus tau minus delta t minus, that's just this, right? And this is just the conjugate of it. You can check, but this is basically just complex conjugate of it. Everything here is inside is the same. Okay. By the way, I forgot to define. So this phi na is a new parameter that I define using, so okay, this is c squared s squared phi na. Okay, this is a complex number, right? You have a lot of this, C1, C plus, and C minus, right? So I just write this complex number as its amplitude and its phase. Okay, so C plus is this, and C minus is the same thing. But this, okay? So that's pretty easy. Now we can, if you substitute this to here, that's how you get this. One, so this C2 minus this is 1 minus s squared plus this Okay, so this is 1 minus this minus omega square, right? And omega square is, you can open it, it's basically just this. Wait, plus, right? Okay. 1 minus. All right. So you define this new phase using this formula, and this amplitude in the front it can be simplified as this. So that's where you get this. Okay. Now we are almost done. So you see that this is just two exponential function, the sum of two exponential function which are conjugated. So the result is 2 cosine. Right? It's pretty nice. It's a great simplification. And if you notice that this is the same, this has the same form. They all have the same form. Right? All right, don't tell me you don't see this. This part all have the same form.
I guess so, yeah.
Come on.
Yeah, it's the same, yeah.
1, 2, 3. 1, 2, 3. Okay? It's not that hard. Okay. Not that hard. We're almost there. Almost there. Yeah. You see, this ends up converged to a very elegant form. So you can factor out these terms for all the 3 terms, right? Yes? You can factor it out. The first 2 terms give you a 2. The second term is a cosine.
You won't have 2 in the beginning.
What?
The 2 in the beginning.
Right, you're right. Sorry. Good. Thank you very much. Yeah? And if anybody is good at trigonometry, how do you call this? Trigonometric functions. You know this formula. 1 plus cosine theta is equal to 2 cosine square. Half angle. Yeah? So you see, this is exactly that. So pretty awesome, right? Pretty awesome. So this factor out, they give us a 2. And there's a 2 from here, this half angle. So in total, we have 4. A factor of 4. Okay. 2. Pretty simple, right? What is better is that this has a very nice physical interpretation. Let's inspect this. Let's write it out. Let me write it out to you like this. Okay. Okay. These are the same, right? Can you convince yourself that these are the same? I'm just S. I just write out the full form of S, and I move this a little bit, just so that it will make my point clear later. And I rearrange this a little bit. Put a minus sign here, and then change the position of t and tau, and this become positive. Okay. All right. Pretty simple. Do you recognize that this is a single slit diffraction? Single slit diffraction envelope. This is called a sinc function. A sinc function is this. This is a sinc function. Okay, and a single slit envelope is a sinc function square. And it looks like this. Yes?
The sine squared is at the sine, not the with is x over x, sine squared x over x.
No.
That's,
The sinc function is sine x over x.
oh yeah.
And here we have the size, we have the square.
Oh, both is square.
Okay, so this is basically a sinc function, and you take the square of it. The sinc function oscillate between 0 and positive, positive and negative. Okay, this is a single slit envelope. Let me draw it. Okay, this is a single slit envelope, right? This is an oscillation. Okay, so a single slit envelope has with an oscillation inside. What is this? Is this form? Does this look familiar to you? This is exactly the double slit diffraction pattern. This is exactly a double slit diffraction pattern. Isn't it beautiful? You see that a double slit has this, 2 holes, right? And when you have a wave when you have a particle, an electron, that go through this double slit, it can be in this hole or this hole. It can go through this hole or this hole. And it's in a superposition, right? So it can simultaneously go through this hole or this hole, right? And the result is a diffraction. That's called a double slit diffraction pattern, right? Why does the Ramsey interferometer have a double slit diffraction pattern. Okay, the interpretation is the following. You offer two pulses, right? Your state, you're reaching to the excited state, right? From ground state to excited state, right? You can get to the excited state by the first pulse, or you can get to the excited state by the second pulse. And the two probability amplitude interfere, and that gives you these fringes. In other words, this is a double slit in time. This is a temporal double slit. Instead of a spatial double slit, this is a temporal double slit. This is a spatial double slit. So here, you can go to the right or the left, or both at the same time. Here is you can be excited a little earlier, or you can be excited a little later, or you can be in superposition of both. You have superposition in time, guys. Isn't that cool? You have superposition in time. We always think time as something that just go, right? So what is past cannot be recovered. Of course, space is, yeah, sure, superposition being this position and in this position at the same time, yeah, I can imagine that. But time is different from space. Time is so much different from space, so that it's really hard to imagine what this superposition in time means. But here we see a double slit analog in time. This is a temporal double slit. Okay, and that's what gives us the double slit diffraction pattern. But what's more, we have a little more. We don't have just these two terms. We have also this term. Okay, and this term is basically the same as the single slit envelope, because it has a omega here and it has an omega in the denominator, right? So it's basically a double slit envelope, and you inverse it, put a minus sign, right? And you shift it up. So it basically looks like this. Sorry. So this is 1 and this is 0. Okay? So it's kind of like an inverted double slit pattern, okay? Except that the width here is different from the width here, okay, for other reasons. Oh, sorry, this is not 0. This is some number that's not 0. But what this does is it gives you a broadening. It stretch out. It gives you a multiplication factor here, but not equal, not linearly. Right? So it's really a little bit like the power broadening thing. So what happened is effectively this broadens the Ramsey, the double slit envelope. Okay, so this broadens the single slit envelope. It becomes like this. It's like flatter on the top. Okay. But you still have the same fringes because the fringe is controlled by this term only. It's not affected. Okay. So you have this. Okay. So I'll call this a broadening. This is a broadening profile. So qualitatively, Ramsey interferometer is the same as double slit diffraction pattern. But quantitatively, because you have this broadening profile, so this is more like a double slit. I would say this is a double slit diffraction pattern. Double slit diffraction pattern with a broadened envelope. With a broadened envelope. Okay? But qualitatively, you can just think of it as a double slit diffraction pattern. All that matter is this term. Everything that is important is this term, and this is the same as the double slit diffraction pattern. The Ramsey fringe, we have the peak height, we have the peak spacing, right? We have the peak width. What is the peak spacing? So in the Ramsey spectrum, what's the peak spacing here? It's 2 pi. So if you remember that our earlier discussion on the Ramsey oscillation and the period, you see there's a square, so you take this. Okay? And that is the time between the tail of the first pulse and the head of the second pulse. So that's this. This is t minus tau. Oh, sorry. No. T minus tau. No. T minus tau is this from the center. No. Yeah. Okay. Sorry. So this is t. This is t. All right. Yeah, t minus tau. Yeah, this, okay. From the back of the second pulse, from the back of the first pulse to the head of the second pulse, that's just this. It's just this separation. Okay? So that's the Ramsey periodicity. You see, there are two contributions. One is the pulse width. Although the pulse width is usually much smaller than the separation, but nevertheless, it contributes. Okay? And there's, of course, the pulse separation. This can be understood as this. If you pull the double slit diffraction, double slit further, your fringe becomes finer. Remember, in the double slit diffraction experiment, if you pull the two slits further away, your fringe becomes finer. And if you put them together, your fringe becomes big. Until when you merge it, the fringe becomes a single slit pattern, right? This peak width, this is what's important to us, right? When we are trying to measure the frequency, this peak width is half because it's defined by the cosine function. So it is half of that. So it's basically half of the period. Okay? All right, so that's it. Okay, that's it. That's all I want to say about Ramsey. And I just want to make a remark that since the phase is very important, if you have a microwave source and you just go by the envelope, like you go up, you turn it up, right? Sine. Okay, so in our lab, the carrier is a sine function. So it starts with 0. And if you turn it up, if you turn it on for tau and you shut it down, and you wait for some time and you turn it up again, you start with the same tau, is the same 0. Will this work?
Yes, because the peak is still just half the way, not 1/4 of wavelength.
No, this won't work. Okay, this won't work because why this doesn't work is, you see, the phase between this pulse and this pulse and this pulse is independent of the separation because it's always starting with 0, right? So it doesn't matter if you move them apart or close. It doesn't matter. That separation information is not taken into the system. It's kind of thrown out. Yeah. So what you need to do is you must have a microwave that is continuously on. Okay. That is continuously on, and then you overlay an envelope on top of it. Okay. So you see, the second pulse starts with maybe a high point or a low point depending on the position of your second pulse. The initial phase of the second pulse depends on the separation. That's what gives you the Ramsey fringe. Okay, so that's very important. You need to have phase correlated. The two pulses needs to be phase correlated, otherwise it wouldn't work. Okay, so that's one very important remark. The second important remark is that there were two difficulties that we encounter with the Rabi spectrum when we try to determine the resonance width of the qubit, right? Who remember what are the two obstacles? Oh, no, those are just the effect. In order to avoid power broadening and avoid transit time broadening, we want to use a low power and long pulse, right? But that wouldn't work because there are two obstacles.
Decoherence and relaxation.
No, decoherence and stability. Okay, there's decoherence and stability. Now, can we overcome decoherence? Well, this is obviously a quantum interference effect, right? So if the second excitation happens at the time when the coherence is already lost, there's no use because the two paths cannot act coherently. There's no superposition anymore, right? If they cannot act coherently, or if they cannot act as probability amplitude, then you don't have this interference business at all, and you don't have the fringe at all. The fringe is lost, okay? And it will just be like another Rabi pulse. They are, so once you, once the excitation, the second excitation, it is out of the coherence time zone, the coherence time window, it is useless. So still, the Ramsey method is limited by the decoherence time. Nobody beats decoherence, okay? Nobody beats decoherence. Decoherence is the eminent of quantum mechanics, all right? So nobody can beat it. However, do we gain anything by using Ramsey? Yes, we do.
What is stability in a more?
Yeah, let me just explain that. So what do you mean stability? Because you just said that, well, I still need to turn on the microwave for so long, right? And I need to turn it on for so long, I just need to put a modulation over it. Well, there's an alternative way you can do this. Instead of having the second, it is possible to have two separate poles. So you really shut down your microwave. You really shut it down. But when you turn it on again, because you know exactly which phase factor is required, right? you know this is the required phase vector. So you need to just add a initial phase to it to make this not go not start with 0, but start with something else. And when this move, that phase is changing too. This phase depends on t. Okay. So you see, I can shut off my microwave if I know how to make the second microwave still phase correlated with the first one. And without this theoretical understanding, I will not know what kind of phase factor I need to put in for the second pulse. Get it? Okay. So that's why I want to explain all this, because see, after seeing all this, now you understand what makes Ramsey interferometry work and what is its limit. And I think that's an important lesson for all of us. All right, so I'm terribly sorry that we have gone over time. Therefore, I prepare very simple quiz questions for you to compensate for my very long lecture.
But right now, the Ramsey is only for finding the P more easily, but you can.
Oh, later you will do more things that is similar to Ramsey. Anything that you do with multi-pulse works the same way.
Kind of time domain variance.
If you know how 2 works, you know how 3 works, you know how 4 works. It's all the same. You just that math that I just did, you just need to do for a longer one. For more segments, that's all. Okay, so the Ramsey is the cornerstone of quantum information processing. Let's put it this way. If your quantum system does not give you Ramsey fringes, don't call it a quantum system, because it is not. All right? There are a lot of devices that claim to be quantum, but they do not display quantum features.
Like
there are a lot of things. So yes, Rabi oscillation is nice, but it's not so. It's not. It takes really deep understanding to understand that oscillation is due to quantum. But Ramsey, because it's so qualitatively different in the spectrum, it has fringes. So it's like a smoking gun to tell if the system is quantum or not. All right, so quiz question number 1. So can the pulse used in Ramsey interferometry start with the same initial phase? Okay? Yes or no? Super easy, right? Okay, just pick your answer, please. Let's save some time. Everybody say no? Okay, start to discuss. Start discuss with each other, challenge each other. Start with, remember, what do you start with when you start a discussion?
I can. You're wrong.
You're wrong.
Yeah.
Even you choose the same answer as me, you're wrong. Okay?
Yeah.
Just start a discussion among your 3.
Why did you choose this one?
But I still don't. I still don't. No, I still don't. Of course, there's need to be phase, but I still don't know the exact phase because of because of the what? Because of the interactive and the real Schrodinger, that thing, the omega 2 to omega 4. I still don't understand that thing.
If you don't have phase, you don't have the oscillation.
I know, but the phase is determined by the omega, right? But in our study, we turn omega into omega plus. But
I mean, like, why couldn't they be the same? Because if you do, like,
Do you have
first
anything
pulse here, right?
to ask?
And then you wait for a while, and then you have the second pulse.
Sorry again.
You know how to remove the
Having the
interferometer
same,
stage? Because
you
it's
could have the
using
same
this
initial
one,
phase
and
here,
It doesn't
I
work.
think it's
but you just
originally
adjust
this one.
Shit.
like the timing.
Okay. 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 I see the question. At that time, we also have another.
Because this is a replacement model.
Do you remember?
Send this picture to me, and then take the one from the other one to here.
Okay.
I will have to contact Colab for this
one is just
problem. Thanks.
one arm. And this one, okay, even though this one is heavy initial phase, so it's still it's possible. Yeah. Okay.
Yeah, but yeah. So
Yeah,
what you said,
yeah,
why can't you answer yes?
Yes. Okay.
Okay, everybody is convinced
that
that the other person is wrong. Good.
It's just like okay.
but then
It's not the only. Actually, we can have like some adding form.
but then there will be no interference.
We have.
Depends on the timing.
Yes.
But that timing is that timing
All right,
is determined.
30 seconds.
That
Because
timing is
it's also like the phase is also affected by this one.
that timing is also determined by the T. This needs to be fixed.
Yeah, if you assume
Yeah,
that
this one fixed, but this one have like you can have different periods. I mean, and sometimes, for example, this one is here, but this one is here. Okay.
it's different initial phase.
Yes.
But if you move
But
this one,
this one, like your first can have the same.
All right, time's up.
Can have another thing.
Time's up. Okay, go back to your line. Anybody want to change? Oh, great. You changed? Good. Finally the discussion is making a difference.
No, we just
but
realized.
we need clarity of the definition of the initial phase.
Initial phase means, so this is the envelope,
Yeah.
right? Initial phase means where you start.
If you start going upwards or if you start going downward, basically.
If you start with the value that is 0,
Yeah.
okay, or if you start with the value that is maximum,
Yeah, okay, that's a different phase. Yeah.
okay, or if you just start a value from something in the middle, just the starting value,
Okay.
that's the initial phase. All right.
All
right. So you guys change side to yes, and he stays at no, right? Good, great. Have another round of discussion, and then we're done.
What do you guys mean?
Oh, it's just like
You can have the value, but it is not in the 360 degree phase.
so
It needs to be different.
yeah.
But we are saying yes, they can have same with the same.
Because he says like it's not too high, right? So because it's not, so it's.
But it's like, but here you see here it starts at like this phase, and here it's a different phase, right?
Okay, let me just add a qualify always starts with the same initial phase. I don't want to take this as like, oh yeah, in a special example I could have the same initial phase. I don't want you to take it as this. Always.
Always start with the initial.
So what do you guys mean? This is a different phase.
Yes, but you could move this envelope so that it's now it starts at the same initial phase. It just depends on when you have this.
Then it won't have. Then it won't even have anything, because then it won't even have anything, because difference between them has another phase difference and not the original T, which has no phase difference on the Rabi
Did
isolation.
you say these two are not the same phase?
It's two ways. One is you try like actually you as here you also try to make the phase different by
Then it won't have anything because this difference is not exactly T. So it won't even have the interference caused by the
Robbie.
I think since you changed the question, now it is.
But by the way, Rabbi is there's a word called Rabbi, but there's one more B. Rabbi. Yeah. Rabbi and Rabbi are different words.
Even if you move it, then the intermediate gap won't fit the Rabbi period. Then it won't even have interference.
Oh yeah, I think you have a point too. Yeah. And now it's also always.
Okay, 30 seconds.
Yeah.
More discussion? If not, then all right, let's choose again. You wanna? Oh, so both of you switch back.
Yeah.
All right, great. I'm glad to see that we're moving somewhere, regardless of your answer. Your discussion make a difference in your decision, and I'm glad to tell you that no is the correct answer. No, they cannot. Otherwise, this will not have any effect, right? You can deliberately make them put them at the same phase, but as soon as you change your separations, that separation should change your phase too, right? And that makes the phase no longer the same. So always, yeah, I was afraid that you might think that. Anyway, so the special case, David, Phoenix, and Simon. Okay, great, good start. All right, second question is a little harder. Okay, is the resolution of a Ramsey spectrum limited by power broadening? If you understand the first part of the lecture, and you appreciate the importance of Ramsey fringes, this is basically Ramsey fringes. Okay, the resolution is defined by the Ramsey fringes. Are they
the distance between the fringe?
Yeah, the fringe, the peak width of the fringe. Okay. So is that limited or affected by power broadening? Okay, think about it. Discuss. And start with. Okay. Oh no, sorry. Please choose your answer first.
Yeah, I'm thinking about what to choose.
Okay. You have 10 seconds. 1, 2, 3, because we need to move. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Yes, 1, no, 2, right? Great. Start with you're wrong and debate. Thank you. You are wrong. Guys, you are wrong. Say it. Thank you, Simon.
Even if we don't have the same situation when we have the Ramsey, we still have the pulses, right?
What pulses?
The power.
but the resolution is calculated by
Basically, the power. This is like original, and this is the Ramsey.
Yeah.
Right? If your power broadening becomes like this, it will simply becomes this.
But yes, okay.
This distance won't change. But the height will change. But this distance won't change.
But won't, for power broadening in the Ramsey case, won't it be like this? Like when it gets broadened in that way?
No, because that broadening.
Say you are wrong. No, you are wrong.
Because that broadening is caused by that is the interference of basically the T and tau. If this stays the same, then it won't change. And omega, of course, but omega is determined by this and this won't change. This is
All right, 30 seconds.
It's just because envelope is bigger.
You don't think you would get it like this?
Yeah, this interference pattern has the power broadening is caused by change in this.
Yeah. But the interference is caused by, yes, but still it's still, you see, no, you're right.
And
Yeah,
also,
I think you're right.
even if it becomes that the distance won't change. The distance
Yeah.
won't change.
Because because this one still exists, I guess. But what causes the up and down here is when we are in or out of phase. Yes. But
In
couldn't
and
it
out
also-
of phase of the microwave.
Yeah, exactly. But couldn't it also be caused by the power broadening in combination with in and out of phase?
Time's up. All right,
Okay, still thinking.
go back to your line.
Go back.
And if you want to switch, you can do it now. Okay, we have 3 in no. All right, we will do it one more round of debate. Start.
Also, because the power broadening is caused by this being 100% in the Ravi, but in the interference it is much lower. So it can all increase, I think.
You mean it doesn't reach? Yeah, it's only. But like in this case, it's at quite high level. But you're right, it's not as high.
Power broadening is then meaning there can be more excited states existing there, but there can be interference.
True, because you only, so to speak, you only charge it halfway, right? To pi half, right? So this is like you only charge it here in the first pulse. You go to
Yes.
50-50. And then in the second pulse, you just barely, in the extreme cases, you just barely reach.
Yes.
30 seconds.
But you can still, that's also the case. No, maybe not.
No, when you increase, there will be also a lot of moving to ground state, a lot of moving to the mid.
But in the top case, it's totally aligned. So when it would be 50% charge, when 50% additional charge, so it would go up to 100 when it's completely in phase.
All right, time's up. Okay. I'm glad to hear that some people say you are wrong today. We need to say more of that in a friendly scientific debate. Okay. Outside of scientific debate, my wife has warned me, don't say you're wrong. All right. It's okay. So the answer is the resolution. Let me the answer is no. Okay. Congratulations. If you noticed that a single slit envelope has exactly the same form as the Rabi probability. So in other words, the envelope, this is Rabi.
Yeah.
And this is within the Rabi, you have these fringes. This is Ramsey.
Yeah.
Okay, so yes. So you're right. When the Rabi gets bigger, it doesn't really matter for these fringes because these fringes are just cosine, right?
Yes, but still, if the Rabi got, then the fringes could go out to edges, right?
Hmm?
If you have a power broadening here, then that would also cause the fringes to get power broadened a little bit.
No. The fringe width, the peak width, and the peak distance are completely controlled by this cosine, which is outside that Ramsey, the single slit envelope.
I see, yeah.
Okay.
I see the math now. Yeah.
Okay, good. All right, great. And by the yeah. Okay. Cool. Let's go to the lab and start today's work. Thank you very much for your tolerance for this unusually long lecture.
I borrowed the keys for weekend
Yep.
lab.
Yeah.
Then how does the process?
So I will have the key put in the plastic envelope next to my door.
Can you save it until Wednesday? Because I might want to be there on Monday, Tuesday.
Okay, sure. I will just leave it.
There, yeah.
I'll leave there for a week. Okay.
Yeah.
All right. So if any one of you need to do experiment, I understand that we have really limited time now. If you want to do experiment at another time, just come in because we have a long weekend.
Perfect.
So just come in and do it. I will just leave it there until next Thursday.
Yeah.
And my office is 711. So there's a plastic bag. The only problem that you might have is that the main door might be locked. The main entrance might be locked.
Yeah, but it was unlocked.
In that case,
Just wait for someone.
write an email to me
Okay.
because I'm coming to work every day.
Even in the weekend?
Saturday, not
Okay.
Sunday.
Okay.
Saturday, I typically come, and Ham lives on campus.
Yes.
So if really there's nobody coming in and out, you can just give him a ring and ask if he can help open the door.
Okay.
Okay?
Because normally I simulate the results previously, so I can understand if the result is correct or not. But today I didn't simulate it first.
Okay. All right. That's we still have 20 minutes until you can leave. All right. So if you don't want to do experiment today, that's fine. But at least I don't know, go to the lab and leave at 6:30. Okay.
I'm going to take the high-speed rail to Tainan. I wonder if it will be a lot of people today because it's holiday. We'll see.
Of course.
Yeah, because I didn't get tickets. I'm just going to line up for the non-reserved. I think it will be less people later tonight.
Okay, and have a great weekend, a great long weekend. I think we also have the day off for Monday, right? Is Monday also off?
No, don't think so.
Okay.
I'm not sure.
It doesn't matter.
Yeah, I don't know. I have to study. Will you stay at campus for a
Yeah,
month?
I'm not taking vacation anywhere. I have too much to do.
Okay.
Yeah. See ya.